Okay, so now we're prepared to talk about the different types of radiation reactions that might occur. The first one I want to talk about is called alpha decay. And in this type of radiation, we have an unstable nuclide that emits an alpha particle. And there's two different ways of writing an alpha particle. One is with the Greek letter alpha, and the other one is with the elemental symbol for helium. And this is kind of unfortunate. I think this is a little bit misleading in some sense. But the reason that we use helium here is because an alpha particle is essentially a helium nucleus. It has an atomic mass number of 4 and an atomic number of 2, so it's 2 protons and 2 neutrons that are being emitted, but there's no electrons, so it's not an element onto itself. And once it emits that, it's going to have a mass number that is 4 less because it removed 4 mass units by emitting that alpha particle. And its Z number atomic number is going to be reduced by 2. And again, we can write it in one of these two forms. We can look at an example down here where we have polonium-210. It emits an alpha particle and is then what's left over is going to be a nuclide with 82, 2 less atomic number, which corresponds to lead, and a mass number of 206. It's somewhat macabre, but interesting to note that this polonium-210 is favored by some organizations, like national organizations, for using to poison people in assassinations. Famously, a Russian dissenter by the name of Alexei Lichtenvenko, can't quite pronounce his name right, was poisoned with polonium-210, and the reason being that this is highly toxic to the body. Alpha emission is very dangerous when it gets inside of your body, and then the leftover material lead is also quite toxic to you. So you do not want to get any polonium-210 inside your body. Another interesting thing to note is that very, very small trace amounts of polonium-210 have been found in cigarettes. So there's even another reason why you don't want to smoke cigarettes. The next type of decay that we're going to look at is what's known as beta decay. In this scenario, we're going to release a beta particle. It's often written with an E, similar to an electron, because a beta particle has a mass similar to an electron, so it's negligible. We're not going to count it here, so it has a 0 mass number. But it's going to decrease the atomic number by 1 and then yield a nuclide that has 1 higher atomic mass number. If you're wondering how this works out, what needs to happen here is we need to have balance between A and Z. So this value here plus this value here needs to be equal to this value here. So if we have Z plus 1, we subtract 1 away from it, we get back to Z. We can also write this particle using a Greek letter beta, and the same thing follows through. If we look at an example down here, we have iodine-131. It releases a beta particle, and it gets reduced It leaves behind a xenon 131 stable nuclide. And beta emission can be thought of as the conversion of a neutron into a proton, right? So we didn't have a change in the mass number, which is the number of protons plus neutrons. We did increase the number of protons. So that means that in order to have the same mass number, we have to have one fewer neutrons. So we can think of this as a neutron that is split into a proton plus a beta particle. Slightly more exotic, we have positron emission. In this case, a unstable nucleus is going to release a positron particle. Again, we write this with this E because it has a mass value similar to an electron, but it has a positive charge. So we've never seen this particle before, but it does exist. It is like the positive counterpart to an electron. And it is going to wind up decreasing the atomic number by 1, but maintaining the same mass number. And again, we might write this using this capital beta here to indicate that it doesn't have a mass value that it's going to be associated with it. So just to review here, positrons have the same negligible mass as electrons, but with a positive charge. Positron emission can be considered the conversion of a proton into a neutron. So you have a proton that turns into a neutron plus a positron particle. If we look at an example here, we have oxygen 15. It's going to emit a positron and then produce nitrogen 15. If we do our math again, we have 15 plus 0 equals 15, 7 plus 1 equals 8, and we have balance across the equation. So the next type of radiation I want to talk about is called gamma emission. And what winds up happening is that during nuclear reaction, there's an incredible amount of energy that's being released. As a result, sometimes the nuclides can be formed in an excited state. And what's ultimately going to happen whenever we see an excited state is that these excited states are going to relax down to what they call a ground state. When this happens, they're going to release energy. In this case, they're going to release energy as gamma radiation. This is very powerful electromagnetic radiation. But it is electromagnetic radiation. So that means that there's no particle that's coming out as we know it. There's no mass to gamma radiation. It is similar to ultraviolet radiation or microwave radiation, infrared radiation. It's just very high energy light radiation that's coming out. X-rays would be another example. We'll write that this nuclide is in an excited state by putting a little apostrophe on it, and we'll show that when it relaxes down to its ground state, it also releases some of this gamma radiation. Producing gamma rays is one of the methods by which we use radiation in the medical field. Sometimes we use materials that produce gamma rays in order to target tumors and things of that nature in order to destroy them. If we look at an example here, we have cobalt-60 in an excited state. It releases gamma radiation and then is now in its ground state, cobalt-60. Note that there is no change in either the atomic number or the mass number for this type of reaction because there is no mass or charge to a gamma ray. The last type of nuclear reaction I want to talk about is what's known as electron capture. And this is a little different than the other forms of nuclear reactions that we've seen so far. In this one, we actually have the absorption of a particle as opposed to the emission of a particle. So in this case, an unstable nuclide is going to absorb one of its inner shell electrons, and then that's going to decrease its proton value. So an inner shell electron combines with a proton to form a neutron. That's what's happening here because we have the same mass number, but one fewer protons, so we had to have created a neutron in this case. And one thing that's interesting about this is that this is often going to result in the emission of electromagnetic radiation in the form of X-ray radiation. This is slightly less energetic than gamma radiation. And this occurs when the electrons that were on the outer part and wider orbitals around the nucleus relax down to fill in the hole that was created when one of the electrons was absorbed, and then one of the outer shell electrons is going to need to be replaced at that point, and this relaxation is going to release X-ray radiation, which can also be dangerous. An example, we have potassium-40. It absorbs an electron and produces argon-40. Another interesting thing to note in the context of chemistry is there's something called the electron capture detector. Because we have really good ways of measuring X-ray radiation, we can create detectors using this phenomenon called electron capture that are very, very sensitive and selective to only certain species that also exhibit this electron capture mechanism. Okay, so now that we've discussed all of the different forms of radiation we want to talk about, let's go over an example problem. When helium-4 is bombarded by an alpha particle, it forms a neutron and which nuclide? So this involves something that I haven't really spoken about yet, which is the fact that it is also possible to not just form a new nuclide, but also to just form a free neutron during a reaction. But we're not going to let that sway us. So we have our basic formula here where we're going to have our reactants, and then those are going to be separated by an arrow, and then go on to our products. So what are our reactants here? We start off with helium-4. We'll write that like that. It's having a alpha particle added to it. It's being bombarded with it. So we'll write plus an alpha particle. We know that this is going to produce a neutron. Neutrons have a mass number of 1, but an atomic number of 0. And then we need a nuclide. So we're going to put in there our symbol for a generic nuclide, and we want to figure out what this is going to be. We know that this number plus this number plus this number, it needs to equal this number plus this number. We need to have balance across. So we'll start off by taking the atomic mass and looking at that individually. So we have 4 plus 4 on the left side, and that needs to equal 1 plus A on this side. We need to solve for A. We do 4 plus 4 is 8 minus 1. A needs to be 7 in this case. Looking at the atomic number, we have 0 plus Z is need to equal 2 plus 2. So we have 2 plus 2 equals 0 plus Z. Therefore, Z has to equal 4. A atomic number of 4 corresponds to beryllium. We can see that on the periodic table. So the nuclide form is going to be beryllium-7. Another way that we can formulate these types of problems is to not ask you for what nuclide is going to be formed, but instead what kind of decay is happening. So in this example, we say, what type of decay does uranium-235 undergo to produce protactinium-235? So we know that we're going to have uranium-235. It has an atomic number of 92. We can get that from the periodic table. It's going to undergo some kind of decay, meaning it's going to emit some kind of particle. We're going to write this generic form of a particle here, plus the resulting protactinium-235. It has an atomic number of 91. We look that up in the periodic table to find that out. And we do the exact sort of balancing here. So if we look at the atomic mass, we start off with 235 for uranium. We wind up with 235 on the protactinium. A needs to be added to this to give us 235, so A has to be 0 in this case, which limits the types of decay that we have. If we look at Z, we have 91 plus Z on this side, and that needs to equal 92. Therefore, Z has to be a positive 1. And we get our positron emission. And it would probably be technically correct to actually put a little positive value right there, just to be sure that we're being clear about what we're doing. And we're having a positron emission because that is the type of particle that has a mass number of 0 and an atomic number of +1.